Okay, so welcome to the next module. So, we have learned till now how to calculate work in a constant temperature, and today we are going to understand that how an expansion or a free expansion, whether it will lead to a decrease in temperature or not. Because remember, we discussed that in the free expansion case the work done is 0, but whether the temperature will decrease or not, that is what we are going to see today. And there was a famous experiment by Joule, who devised an experiment to understand that whether a free expansion will lead to a change in temperature or not, and followed by another one called Joule-Thomson effect. So, first today we are going to talk about Joule free expansion process. So, the free expansion process is designed in such a way that in there are two chambers in an isolated system. So, this is an isolated system, which means that total energy will be conserved, or an isolated system will not allow any heat exchange to go on in or out. So, there will be no exchange of heat, and initially the gas molecules are confined to one side of the chamber, right. So, this is what is preventing it, and then at some point this stopper will be removed and the gas will expand to the full volume. Now, in that particular case, what do you think will happen to the temperature? Will it decrease? Okay. So, why do you think it will decrease? Okay. So, let us see now. Let us say we know from the first law of thermodynamics that du equal to dq plus dw, right. Now, I said that the system is an isolated system. So, basically this whole chamber is isolated. Okay. This is an isolated chamber, which means our dq is going to be 0. There is no exchange of heat going in or coming out. So, and we know that a free expansion process dw is also 0, right. So, du is going to be 0, right. Now, if d is going to be 0, then do you think the temperature is going to decrease? So, this is what we are going to understand today, okay, what is going to happen in this particular process. So, let us now expand the du. So, again I will remind you that u we can expand as a function of volume and temperature. So, therefore, we can write total differential du in terms of both v and t, du by dv t dv plus del u by del t v dt. Now, since in this particular case our total change in u is 0, we are going to put that on the left hand side. So, 0 equal to del u by del v t dv. Now, when I write dv, I have already used a condition. That condition is du is 0, this du is 0, right. We have used that condition. In order to denote that we are using that condition, we are going to use this subscript u, that it indicates that dv at a constant u, okay, plus del u by del t v dt u. Okay. Now, we are going to rearrange this equation. Now, you know that du by, okay, you know the one of the quantities you know. So, del u by del v t dv u plus du by dt v you know as Cv, right, Cv dt u. So, no assumption, nothing has been used till now in this derivation. Now, we are going to rewrite this equation on the left hand side by taking this particular quantity on the left hand side. So, it will be minus Cv dtu is equal to del u by del v t dv u. Okay. So, we are trying to understand that how much change in the temperature is going to happen if the volume expands in the condition that u remains constant. Okay. That is what we are going to observe. So, now we rewrite this equation by dividing both sides by dVu, we divide both sides, remember. So, minus Cv, when I divide both sides I can write that as dt by dV at a constant u is equal to du by dV at a constant t. Now, this quantity del T by del V at a constant u is called Joule's coefficient, that I have mentioned here on the top. You see, Joule's free expansion gives us this quantity. So, remember the right hand side quantity del u by del V at a constant t is not possible to be obtained in experiment, because there is no way to measure internal energy. We can see a change in enthalpy and things like that, but one cannot measure it directly. Rather, it is much more easier to devise a system in which there is no exchange of heat and therefore, u can be conserved. We can measure the temperature before and after expansion, and thereby we can calculate the quantity N j, and once we have N j, we know the C v, we will be able to calculate the right hand side quantity. You will see often in thermodynamics that we will use this kind of partial derivatives, and often it looks like that they are there to give us pain. I used to think that way. However, the reason is that these are there to relieve us from the pain, because if you want to observe or measure certain quantity, we can always relate it to something else, and thereby we can get the same thing, which means that in order to see that if I change the volume keeping the temperature constant in an isothermal condition, how much change of u will happen, I can get that by knowing two things, C v and del T by del V at a constant u. That is the sole purpose of having this relation. So, I can write now my N j or C v N j is del u by del V at a constant t, or N j is minus 1 by C v del u by del V at a constant t. So, this is the quantity. If we calculate that by knowing N j, we will know, I will remove this right hand side, whether there will be a change in the temperature or not. What is this quantity del u by del V at a constant t for ideal gas? So, ideal gas we know that u equal to 3 by 2 kBT, right. So, del u by del V at a constant t is going to be 0, because u does not depend on volume. So, when I change the volume, if my temperature is fixed, then u is not going to change, right. That is what this particular quantity tells us, right, that if the temperature is same, u is going to be always same, whether you change the volume or not. If u would be a function of volume, then only u will change when volume is changed, but if u is not a function of volume, then how is going to change? So, for ideal gas, therefore, N j is minus 1 by C v into 0 is equal to 0. So, Joule's coefficient is 0 for ideal gas, which indicates that when we will lift the stopcock or stopper, then the gas will expand. However, for ideal gas there will be no change in temperature. So, free expansion of an ideal gas does not change the temperature. So, we understand from this, right. Now, question is that will that happen for actual real gas also or not, right, and we have to understand that, right. So, before okay, so if we want to understand that, let us go here, let us try to take an easier example, which is a van der Waal gas. P equal to R T by V minus B minus A by V square, we know that. So, let us keep this equation of state in mind and try to calculate the quantity that is required to calculate the Joule's coefficient. We derive Joule's coefficient N j as minus 1 by C V del u by del V at a constant t. So, this is what we are going to calculate, right. How we are going to do that? Because this above equation does not give us any information about u, right. So, how we are going to do that? Any idea? Because if I have to use this, remember what is the left hand side? Left hand side is del t by del V at a constant u, that is equal to our N j. So, that this left hand side is also not possible to calculate, because how do we guarantee that u is going to be constant? And here also it is difficult because we do not have an expression of u, we only have an equation of state. You will learn later that this equation of state is actually a derivative of a fundamental equation, that means derivative of u already. So, how do we get that? So, in order to get that we are going to use some tricks. In order to do that, I am going to do some derivations which you are not going to understand right now, because I am skipping some steps here. So, once we learn those things, again we will do the same thing. Okay. So, let me do that quickly. What I am going to tell you for the time being is that del u by del V t can be expressed in terms of this relation. How we are arriving at this relation, you will only come to know after we cover the second law of thermodynamics, and we introduce some quantity called entropy and Maxwell's relations. However, it is important to show that how this is going to affect, and therefore, I am going to just show you the relation. So, for the time being you just accept this formula as is, you are going to learn that very easily, it is not a problem. So, now we know that del u by del V t can be expressed in terms of this relation T del P del T V minus P, and we know from equation 1 then how to calculate del P del T. Let us calculate that. Del P del T V is a derivative of the equation 1, which is R by V minus B. So, therefore, from equation 2 we get del u by del V t is equal to T into R by V minus B minus P, and P is R T by V minus B plus A by V square, which is A by V square. So, therefore, N j is going to be minus 1 by C V A by V square. Now, you remember A was positive or negative? We have discussed about A for helium, hydrogen and lot of values. A was a positive quantity. Since A is greater than 0, C V is greater than 0 and V bar square is obviously greater than 0 because it is a square, your N j is going to be less than 0. Now, if N j less than 0, what does it mean? That if V increases, T decreases. I already told you that A denotes the strength of interaction between the particles. Higher the value of A, lower the temperature decrease, or lower the decrease in higher the decrease in temperature will happen. So, because what happens is that physically speaking, that when the particles are close together, so when you increase the volume, the particle will have to go apart from each other against the strength of interaction between them, and that the work that they will do will actually reduce the temperature of the system. Okay. So, we can see that even for a very simple system like van der Waals gas, where we put interaction, we see that an expansion will cause decrease in temperature. And remember our Big Bang story. So, our universe is an isolated system and it expanded. So, while expansion, two things happen. So, one is that conversion of energy to matter, which will of course reduce the amount of energy of the system, and a volume expansion in which things will go far apart from each other, which will reduce the temperature of the system. So, it is not like an adiabatic process, it is an expansion, because for an adiabatic process you will come to know that we are going to talk about adiabatic process, you will come to know that it has to push against some external pressure, but our universe is some system where nothing is there beyond that. So, you can think of that as an expansion that is happening, which cools down the temperature, just like a Joule expansion process. Okay. So, so we see that is what is happening. Now, we are going to talk about, so this is a process that happens at constant internal energy. Now, similar to that, there is Joule-Thomson effect, which talks about constant enthalpy process. Okay. So, we talked about constant energy process, now we are going to talk about constant enthalpy process. So, in order to do or observe the change in temperature due to change in pressure. So, earlier there was change in temperature due to increase in volume or change in volume. Now, we are going to talk about change in temperature due to change in pressure, and you see that it has to be done in such a way that overall enthalpy remains constant, just like in earlier case the overall energy was remaining constant. So, that is the difference between Joule's expansion or Joule's coefficient and Joule-Thomson coefficient. In one case U was constant, another case H is constant. Now, this device that you see here in fact makes the enthalpy constant. How we are going to talk about? So, let us say our initial system is such that there are some gas particles here, there are gas particles here at temperature T1 and pressure P1, and this is the piston that is going to be pushed, and this is a this place is a this place is the porous region, this is the porous region. When you push the system up to this much point, all the gases will go on the other side, and initially this piston was here and then it has gone up to this much. Is it clear now? So, initially the gas was on the left chamber at temperature T1 and pressure P1, you push the gas through the porous membrane to the other side, creating different temperature T2 and different pressure P2. In the process, the volume became from V1 it went to 0, and in the right hand side the volume from 0 it went to let us say V2, correct. Now, let us see what happens in this particular situation. Okay. Again let us again our overall system, the whole system is kind of isolated. So, again we will use the first law du equal to dq plus dw, but since dq equal to 0 it is just dw. Now, we have to calculate what is the work done in the whole process. So, let us say in the whole process the change in internal energy is u, and we have to calculate the amount of work done W. So, W in the first step when it goes from V1 to 0 is how much? What is the external pressure that it is dealing with? P1, right. So, minus P1, it goes from V1 to 0. So, 0 minus V1, okay, because final volume minus initial volume, and in the next step the external pressure is P2, because that is the final pressure that is going to be there. So, minus P2, and it goes from 0 to V2. Okay. So, the total work done is W1 plus W2, and we can write that as P1 plus P1 V1 minus P2 V2, right, and that is our delta U. Now, delta U, let us write that as U2 minus U1 is equal to P1 V1 minus P2 V2. Now, rearrange the equation, U2 plus P2 V2 is equal to U1 plus P1 V1. Now, is it familiar? It is enthalpy. So, U2 plus P2 V2 is H2 and right hand side is H1. So, that means that enthalpy in this particular whole setup is constant. So, now once the setup is there such that the whole process enthalpy is going to be constant, but pressure is changing, we want to understand how much change in the temperature will take place, right. So, for that what we are going to do is that we are going to write it here H as a function of P and T. Remember, I will just remind you again that we can write in whichever variable we want to, however, naturally P and T are going to be important for H. So, let us write the overall thing del H, we are going to do the same way, you can see that del H by del P T dP plus del H by del T P dt. Now, since our enthalpy is constant, so it is going to be 0, and now we are going to indicate the P with H in order to denote, and you know what is the del H by del T P, right. What is that? Del H by del T P? Cp. So, just straight away write Cp dt H. Rearrange the equation, minus Cp dt H equal to del H by del P T dP H. Divide both sides by dP H is going to give you okay. So, what we are seeing here on the left hand side, that how much change in the temperature happens due to change in the pressure when the overall process is done at a constant enthalpy, and this is the quantity that is called Joule-Thomson coefficient. So, minus Cp mu is del H by del P T, and minus Cp mu is called isothermal Joule-Thomson coefficient. Sometimes that is also measured, and in that case it is nothing but del H by del P T. That means, change in the enthalpy for a change in pressure at a constant temperature. Okay. So, you can measure either you can measure either mu or you can measure mu t. They are not same, because there is a Cp sitting here and the Cp may or may not be temperature dependent. So, you do not have to worry about Cp if you are calculating only the mu t, because then it is already taken into account. Okay. So, what you are going to calculate, basically you are going to calculate the change in temperature due to change in pressure. So, often what happens is that in laser experiments where you want to have a jet cooled spectroscopic technique, where in high pressure the gas comes and suddenly it goes to a larger space where the pressure is very low and the temperature goes down very much, and in that very low temperature there will be a formation of dimer and trimer. So, in our institute, Professor Alok Das works on spectroscopic techniques using this particular Joule-Thomson effect. Okay. So, now that we know this one, we will just go back, just remember that then mu t is del T this. So, I will just compare that with our Joule coefficient here itself. Joule coefficient was Nj, and Nj was minus 1 by Cv, instead of Cp it was Cv, del instead of H it was U, instead of P it was V, that is it. So, you can see U and V are going together, H and P are going together. Okay. Correct. Okay. So, the question is that in both Joule's case and Joule-Thomson's case, both pressure and volume are changing. So, what is the difference? The difference, as you can see, mainly is in that first process in Joule's case, total internal energy is constant, and whereas in Joule-Thomson case total enthalpy is constant. So, that is the main difference, and the main variable that you are looking at is pressure in the case of Joule-Thomson, because you want to see as a change in pressure how it is happening. So, if the pressures remain same, even if the volume changes, you are not going to see any change. So, it is basically what you want to measure, and you see this is a setup in which the gas comes at a high pressure and then goes through this particular porous region, this yellow color, and then it goes to a larger volume at a low pressure. Now, I would like to ask you, okay. So, before I ask you that one, let us write down once more that mu is del T del P H, which is minus 1 by C P del H by del P at a constant T, right. I remember that by correlating with what was for joules. If you by chance forget the formula, you can correlate with one of them and then remember. Now, what is the value of mu in case of ideal gas? How do you calculate that for an ideal gas? Can you tell me how to do that? Because Cp is certainly not going to be 0, it is a positive value for ideal gas, and you already know that Cp value for ideal gas. Cp is Cv plus R, Cv is 3 by 2 R, so Cp is 5 by 2 R. So, we have to calculate del H by del Pt, right. So, we know that H is equal to U plus Pv. So, del H by del P at a constant temperature is del U by del P at a constant temperature plus P into del V by del P T. Why did not I do del P? Because that will be is it correct? Oh, I am doing that. So, plus V del P by del P at a T. Okay. Now, del P by del P is basically 1. So, I can write that as V. So, del U by del P T plus P del V by del P T plus V. Now, what will be the value for that at an ideal gas? So, we have to calculate this quantity, we have to calculate this quantity and this quantity, okay, in order to do that. So, I will need a larger space. So, I will go back and do that once more. So, we have to calculate del H by del P at a constant temperature for ideal gas. So, we know that H is equal to U plus P V. See, we are not remembering anything, we will just start from scratch and do that. So, del H by del P T del U by del P T plus P del V by del P T plus V del P by del P T del U by del P T plus P del V by del P T plus V. Now, we have to see what is del U by del P T, correct. So, remember what we are doing like last time, del U or rather du can be written as in the function of both V and T as del U by del V T dV plus del U by del T V dt. Now, I can take the derivative with respect to pressure at a constant temperature on both sides. So, del U by del P T is del U by del V T del V by del P T plus del U by del P, which is C V del T by del P at a constant temperature. Okay. So, here is the interesting thing that comes when I do the derivation. You see what happens? You see that del U by del V T we already know to be 0, right. So, therefore, the whole term is going to be 0 and del T by del P at a constant T is what? 0, right, because we are trying to take a derivative of temperature at a constant temperature. So, that means the whole term is going to be 0. So, therefore, just to use a different color, this is going to be 0. Now, what I am remaining with is this 2 quantity. Okay. So, therefore, I am going to erase this part and then calculate that quantity. Now, what is del P del V? Del V del P at a constant temperature. What is that? Remember, P V equal to nRT. So, therefore, V equal to nRT by P. So, del V del P, that means I am taking a derivative with respect to pressure at a constant temperature. nRT is fixed, right, into minus 1 by P square, correct. And what is nRT? nRT is again PV, right. So, PV by P square, so minus V by P. So, I am going to put that. So, del H by del PT is equal to P into minus V by P plus V, which is giving me minus V plus V 0. So, which means that for an ideal gas, the Joule-Thomson coefficient is also going to be 0. Now, do you think that for a real gas, the temperature is going to decrease or increase when you go from high pressure to low pressure? Because we saw that when you go from low volume to high volume for van der Waals gas, temperature decreases. What happens from high pressure to low pressure? Will it decrease or not, or will it increase, or will it remain constant? For ideal gas, of course, both will remain constant. I am talking about real gas, and since real gas is difficult, we can take van der Waals gas as an example and try to understand what is going to happen, right.